Ready, set, go. Okay. So we already talked about these terms. A proton is an H plus that's kicked off. So if you have an acid that's monoprotic, it means it can only donate one proton, one H plus. Polyprotic means it can donate more than one proton. And do you remember the H2SO4 sulfuric acid? I said those H2 actually can kick off both of those protons. So H2SO4 is an example of polyprotic acid. And then we have something that's kind of interesting. It can actually accept a proton or donate a proton. And they call that amphiprotic. Like if you're ambidextrous, yeah, I think I mentioned that the other day. And we'll look at some examples of that. So it can accept or donate a proton. So if it is an acid that has potentially two protons to kick off, the first one's going to go a lot easier than the second one. And if Ka is an indication of how easy it goes, the higher the Ka, the easier it goes. So the first ionization will have a high Ka. And this says the Ka for the second ionization will be less. Makes sense. So oftentimes the second one to go is so negligible that the acidity of the solution is just from the first one, the first ionization. So, and we're going to kind of talk through, I think we're going to do it with sulfuric acid here in a minute. Yep, here we go, sulfuric acid. And I think I'm going to kind of do this up here on the board. So polyprotic acid, but this is kind of a different polyprotic acid that you're going to do for your homework, because this actually, the first one's it's a strong acid. Okay, so the exercise is in italics, what we're going to do. Basically, we're going to take this 0.10 molar solution as it was prepared, H2SO4, and we're going to see what the H plus, the hydrogen ion concentration is with both ionizations. We're going to add them together. So it looks like this. So the first one, okay, sulfuric acid is one of the 6 or 7 strong acids you need to memorize. It looks like this. H2SO4, strong acid, one-way arrow. It goes into H plus HSO4 minus. Okay, this is the hydrogen sulfate ion. So just for kicks, make sure we're all on the same page. We said that this is 0.10 molar, right? So in this case, this is 0.10 molar. Do you buy that? Okay, good. And this is also 0.01 molar. So we'll call that ionization step 1. Ionization step 2 basically takes this guy and it says, all right, we're going to make it donate that proton. So here we go, HSO4 minus. Now this is actually a weak acid. So when it donates a proton, now it turns into the sulfate, the hydrogen proton of the sulfate ion. Okay, so that is ionization number 2. So notice that this is actually, there's a Ka value for this equilibrium, and we could write the Ka expression. It's the molar concentration of the products, H plus and SO4, 2 minus, divided by the molar concentration of the reactant, HSO4 minus. And we have a Ka of, it's pretty high, 0.011. So kind of what we're trying to do in this problem is basically we're going to come up with the overall hydrogen ion concentration. We're going to take this hydrogen ion concentration plus this hydrogen ion concentration. But the problem with this is this gets a little interesting. I'll kind of talk you through that too. So here is the table that we've looked at before. This is actually just polyprotic acids, like the title says. So down here, we have the one we're dealing with, sulfuric acid. Notice that they're showing a two-way arrow here, but they're saying that the Ka is very large. So I would show it as a one-way arrow. And then this is this right here. And you can see the trend. If you look at phosphoric acid, H3PO4, it's polyprotic and it can kick off all three hydrogens. But if, what's that?
I don't see that one.
Yeah, it's right here. This guy right here.
Oh, okay.
Yep. And so if you look at all three of these Kas, notice they get smaller and smaller as you go on to the next, kick off the next proton. So, so this says for the first step, we're going to assume 100% ionization, so we get, that's the molar concentration of this one. This is the guy that is harder to get to. So to get to this molar concentration, we're going to do an ice table, and I'll show you what that looks like. Let's go ahead and kind of think through that. I'll put that one over here. So the ice table is going to look like this. I'm not going to rewrite that, but I'm just going to make my columns. So this is the reactant, this HSO4 minus. That is our weak acid. And then we have a column for our hydrogen ion, the product. Then we have a column for our sulfate ion. We have initial, change, and equilibrium. So this actually says, well, let's go ahead and start filling in initial. So initial of this, does it make sense? It's 0.10, excuse me.
Yeah.
Okay, good. And usually when we look at an equilibrium like this, we say that there's no product, okay? But in this case, we have a common ion that came from the first ionization for the hydrogen ion.
Okay.
So instead of being 0, this guy is,
That was the same.
yeah.
Okay.
So what would this concentration be, though?
0.
Very good. Perfect. You got it. Now this is one where we know the Ka, but we don't know any equilibrium concentration. So we're going to have to use X as the variable.
Okay.
So for that second ionization, does this make sense? The stoichiometry is 1 across the board. So this would be minus X, and this actually would be plus X. Good, plus X. And so equilibrium concentration is 0.10 minus X, 0.10 plus X, and just plain old X. And now we have that Ka over there. We can plug in these equilibrium concentrations. In the top, we have the molar concentration of the hydrogen ion at equilibrium, 0.10 plus X times X. Okay. Thank you. Perfect. And then in the bottom, we have 0.10 minus X.
Wait.
Yeah, this is a plus X. Does that make sense? So this is all on the next few slides, but let's go ahead and finish this thought. And we really have a Ka value, remember from the table? That's 0.011. So,
We got that from the table.
yeah, we got that 0.011 from the table. It was like 1.1 times 10 to the minus second. Yep. So now let's go ahead and apply the simplifying assumption. And remember how this goes. It says if X, which is the amount of the weak acid that ionizes, if X is sufficiently small relative to the molarity we start with, 0.10, then actually in this case we have two quantities that kind of fall into place. I know. It is nice. Then 0.10 plus X is equal to, so that's small, so that makes that 0.10. And 0.10 minus x is approximately, oops, I got that wrong, plus x minus x. That's also approximately equal to 0.10. Make sense? Awesome. So now check this out. This becomes 0.10, and this becomes 0.10. This whole quantity
One
here.
X variable.
What's that?
And one X variable.
So yeah, you just have x up here is equal to, and that's it. So these two, this is 0.10, this is 0.10.
Oh, they cancel? Oh, nice.
So in this scenario, then x is equal to 0.011. That's it.
Oh, I guess that makes sense if you're dividing by the same number, it's only one.
Uh-huh. I like it. So I have slides that say basically the same thing, what we just did. Okay, so here is, I'll let you kind of fill in. This is kind of stuff we put on the ice table. We're going to let X be equal to the moles of HSO4 minus that ionize. That will also be equal to the moles of H plus formed during the second ionization, and that will be equal to the moles of sulfate that's formed. And then that last set of numbers are our equilibrium numbers. Then that equilibrium, our hydrogen ion is 0.10 plus X because of the common ion effect. The sulfate is X. And the weak acid left is 0.10 minus X. Makes sense? So if we apply the simplifying assumption that we've been doing, if X is less than 0.10, then those two quantities, then they become 0.10. And it's not on here, but it's on the slides, but it's kind of on the board that I could have been a little more explicit on the slides. We said in that case then, this quantity becomes 0.10 and this quantity becomes 0.10. And they cancel each other out, and you get X is equal to 0.011. But there's a little, and that's how I would work this problem, but there's a problem with this problem, okay? The whole assumption I said that X needs to be greater than 100 times Ka in this case. So if you take 100 times Ka, you get 1.1. And the molar concentration is 0.1. So it actually fails that.
Oh.
Yeah, so the simplifying assumption is, yeah. So this number right here, somebody behind the scenes used the quadratic. Somebody behind the scenes took that mess up there without applying the simplifying assumption and came up with the value of X using the quadratic equation, flattening it out and everything. And instead of 0.011, we get 0.0092, which is a difference of what, 0.009? 0.009? 0.0009. Final answer. 0.1239. Does that look right? Yeah. Okay. So this is what we call the exact solution of X, and this is using the simplifying assumption. Now on the test, you're not going to have to use the quadratic. So assume that you can apply the simplifying assumption. So in fact, I'm going to show you then how it plays out. So remember, our goal was to come up with what is the pH of the solution. If we come up with the hydrogen ion concentration brought by both of these ionizations, And we've got this is 0.011 or 0.0092, right? So basically what you're seeing here is adding these two quantities. So if we're adding, we round according to decimals, and we're limited to just 2 decimals because of 2 decimals here. So when we round according to 2 decimals, okay, you get, instead of the first ionization brought you a molar concentration 0.10, you get 0.11. Okay, so that would be the answer. And you would get that whether you went with, I should go here, you would get 0.11 regardless of which one you went with. Okay, so, what's that? Okay.
I was like, that's the let you know, or that's the, I was thinking that was the pH, and I'm like, no.
Not quite.
We haven't done that yet.
Right.
Okay.
So that's the molar concentration of the hydrogen ion. So pH, we use the log function. So we take negative log of 0.11, and we get 0.96.
I'm sorry. Can we go backtrack? So I was thinking of something else when you were saying that we got that molarity, so we would have gotten it either way.
Oh, yeah.
And some of it.
Okay, so,
So,
go ahead.
so if we didn't get the exact, we still would come up with the same answer.
Right.
Okay.
Yep,
Okay.
yep.
Okay.
So regardless of doing this one or this one, you get a total
Okay.
molar concentration, yeah.
So then how, is it generally for problems like this important to get the exact answer? Or I guess it totally depends on the molarities you're working with.
Yeah, it depends on the molarities you're working with. And in this case, well, it kind of like the background leading up to these slides said, the first ionization is a lot more than the second ionization, which will be more than a third ionization, which will be more if there is a fourth ionization. So you kind of, by the time you get to the second ionization, it's kind of lost in the weeds compared to what the first ionization was.
So I guess what my question is pretty much from the second ionization on, can you pretty much use the simplifying assumption for the most part?
In problems like on your test, you can. If this, I was thinking just a minute ago, if this was homework and you weren't looking for the sum of the 2 ionizations, if you were just looking for the ionization that's brought, or excuse me, the hydrogen ion that comes about because of the second ionization, you would have to round, I mean, then 0.011 is different than 0.0092. You know, if that was the question, then I think then you'd have to use the simplifying assumption because they're 2 different numbers.
Yeah. Okay.
But since the question was, what is the overall pH?
Okay.
And this is a little bit different. Well, I'd have to look back at that table that had the polyprotic acids, because 0.011 is still pretty high. And that's kind of the problem we're running into. When it's pretty high, you take 100 times it and, you know, yeah. So, yep. Very good. So this little thing in italics says, if you were to take the negative log of 0.10, you get 1.00. So in other words, this gives you a pH equals 1.00. This down here gives you a pH is equal to 0.96. Okay, so as far as pH values, that's kind of an interesting thought too. Let's go back. I'm going to look back at that table. this one. So like these, you know, it looks like the Ka of the second ionization, that's what you use, 0.011. That's still pretty high. If we look at sulfurous oxide, H2SO3, you know, I don't know. I'm trying to eyeball. It's interesting to think about if you would meet that criteria of 100 times depends upon the molarity of your initial acid. Interesting. Okay, so yeah, this one will be due for sure, and then we'll see how far we get into the next part. Okay? I know you're not stalling. It's not like you, Marie.
No.
So, as you might imagine, this one is a polyprotic problem. So, I do have some hints. Let's see if I can find them. There it is. Okay. So this one deals with the polyprotic acid H2CO3. Carbonic acid, I want to say. So it gives you the initial molarity, and it wants you to come up with the, I think in my hints for A, I'm going to say basically A is this. You have to look at both ionizations. For B, it's actually analogous to finding the molar concentration of this at equilibrium, because it's like, and then for C, it's finding the molar concentration, which is analogous to your sulfate ion. Okay, so here's my hints. Second ionization looks like this. And you can look up those Ka values depending upon your eyesight on that little table there.
Well, there's that, like here in the study section, there's this.
Oh, dang, cool.
Yeah, it doesn't have all of them, but there's a lot.
I didn't realize that. That's neat. So 2 ice tables, because the first one is in equilibrium too. Let's see, one for each ionization. What's that?
Because it's weak acid.
Because it's a weak acid. Don't forget the common ion effect. So the H pluses that are created in the first ionization need to show up as a common ion in the second ionization.
Okay.
I think that's the only common ion you're going to run into. Yep, so my hint for A is to add up the hydrogen ion concentration for both ionizations. For B, you're looking at the equilibrium concentration. So basically B is HSO4 minus. And for C, you're looking at the sulfate ion concentration, which their X is, so that'd be 0.011. Yeah. Yep. And remember, for the HSO4, which is analogous to HCO3, I think if you round to 2 decimals, you're going to get 0.10. Well, let's see. No, you get 0.09, wouldn't you? If you put in X in 0.10 minus X, and X is 0.011, you get 0.09. But then again, I think what you're going to find is this one's going to be your simplifying assumption. This one, your simplifying assumption is going to do fine. So, all right. So, let's take a look at this.
And we're not going to deal with these other two.
What were those other two?
The bisulfate ion, an example of
Oh, yeah. Okay, good. Thank you for reminding me. Yes, let's take a look at those.
Okay.
So, amphiprotic is something that can accept or donate a proton. So, does it make sense? Does it kind of look like that could actually gain a proton and be H2SO4, or lose a proton and be SO4 2 minus? And which way it goes kind of depends upon its environment. And so, of course, the most common amphiprotic substance, we've seen water donate a proton to become the hydroxide ion and accept a proton to become the hydronium cation. So, yep. Okay. So, conjugate acid-base pairs. Basically, what they mean is you look on either side of the equilibrium arrow and you find a pair of species that differ by a proton. And the one that's giving up the proton, you would call the acid, and the one, you would call the acid, and the one that's accepting a proton, you would call the base. So in this case, and you would call them a conjugate acid-base pair. So does this make sense? And sometimes, like right now, I'm looking at it, really? So this one, as it goes over there, it donates a proton, so it's acting as the acid. I won't put weak acid. I guess I could put weak acid because it's a two-way arrow. This one over here, it's accepting a proton, so we call this the weak base. And a lot of times when we get going, I just kind of put an arrow over two that connect. They differ by a proton. Acid-base pairs. So sometimes I get the term acid-base pairs I prefer because instead of saying that this is the weak acid and this is its conjugate base. I don't know. Yeah. But that is a legitimate way, and I guess sometimes I do call that. This is their conjugate acid-base pair. This is the acid. This is its conjugate base. But see, to me, it's kind of going back and forth. So are you going to go for left to right, or are you going to go from right to left again? Okay. Oh, see, there we go. This is the base, and this is its conjugate acid. Conjugate acid-base pairs. So these are all, if you look at each one individually, they differ by a proton on either side. So these are examples of conjugate acid-base pairs. Kind of going from left to right, this is the acid, this is the conjugate base. This would be, let's see, this is in the next one, it's a proton donor, proton acceptor, so again, acid conjugate base. And again here, this is a proton donor, this is a proton acceptor, so we have acid conjugate base. Okay, from left to right, acid conjugate base, acid conjugate base, acid conjugate base. If you're like me, are you like, well, this looks weird, that last one, doesn't that look weird? Because you know that is actually a strong acid. You're like, what's with the two-way arrow? Well, that's a good question. We know in reality it goes one way to a large extent. And actually this one you might recognize as nitric acid, and it was one that you need to recognize is a one-way arrow.
Well, I guess, I mean, it makes sense because there's no hydrogen in the conjugate, so it can't go back because there's
Well, it could grab on to a hydrogen if it's in water, abscond onto a hydrogen and water molecule.
I guess because all of the other examples that were not weak all had another hydrogen. So like the hydroxide and the water and the HSO4 and the NH3, they all have like another hydrogen to go back the other way.
Okay.
But the HNO3 and the HCl don't have a hydrogen to go back. Is that?
Well,
That's not necessarily a thing, that's just coincidental.
I think so.
Okay.
I think so. I do see what you're saying. And in this case, we're not really writing the hydrogen on the product side. So I don't know if this helps, but like we could write an H plus here, Okay, this is actually showing it being kicked off. Okay. And we could do that for over here too. H plus.
I'm always trying to find a pattern, so it's,
Yep.
and that was the pattern
Yeah.
took me,
Yeah.
but it's not necessarily.
Not necessarily.
Okay.
But I would just kind of clarify, yeah, these are both strong acids.
But, so they're still a pair even though they don't
Mm-hmm.
go into, okay.
Yep. Even though they don't both go both ways. Yep. I know. So we have this neat relationship between, when you look on either side of usually an equilibrium sign instead of a one-way reaction arrow, but when you find your conjugate acid-base pairs, there's a Ka for your acid and there's a Ka for your, excuse me, a Kb for your base, okay, for the pairs. If you take the Ka times the Kb for that pair, that's always equal to Kw. Is that not cool or what?
In an aqueous.
Yes,
Okay.
in an aqueous solution. Yes, very good. Yep, I just think that is so cool. And I have a little proof to kind of show you why that works. Okay, I think it's wonderful. And actually, if you want to put a star next to that, I'll even tell you when you use it. I'm going to say use this if you know, I'll say if you know either Ka or Kw, sorry, Ka or Kb, and need the other one. And need the other one. This will ring a bell when we talk about buffers. So use that relationship between a pair, conjugate acid-base pair. Okay, so the other day we talked about water basically falls apart, and it's called autoionization to form the hydrogen cation and the hydroxide ion. And that actually, that equilibrium is kind of where Kw comes from. And I said to memorize Kw to 4 sig figs or 3 sig figs, but 4 will cover you more. So coefficient coefficient 1.008 times 10 to the minus 14th.
Can I ask a question? Does that have, that reminds me of the molecular weight of hydrogen. Does that have any connection, or is that just totally coincidental?
Just totally coincidental.
Okay.
A good way to remember
That's
it.
how
Yeah.
I remember it. That's, yeah.
It is. That is totally coincidental. The coefficient of the Kw, and that's at 25 degrees, so it's temperature dependent. That is for hydrogen. It's 1.008. I'm thinking, aren't you? Times 10 to the minus 14th. Okay. So I'm going to kind of show you. For on either side of the equilibrium arrow, if you pick out the conjugate acid-base pairs, their Ka times the Kb is equal to Kw. I'm going to kind of do a little proof. Okay, so here we go. This is showing the ionization. This would be like a weak acid ionizing to form H plus and B minus, and the Ka expression would be this, right? And this is actually showing a weak base, where if we take B minus, it's going to abscond onto a hydrogen of a water molecule to form HB, okay, and the hydroxide ion. So if we go kind of back and forth, here we have conjugate acid-base pair. They differ, oops, sorry. Here we have a conjugate acid-base pair. They differ by a proton. And here we have a conjugate acid-base pair. They differ by a proton. Now, assuming, and it's not too hard to assume, that actually you have the same species as B minus, okay, you are actually talking about, how do I say this? You are talking about this Ka and this Kb are the, that is the Ka of the conjugate acid, and that's the Kb of the conjugate base. They are a pair. Okay, cool. So I said if you multiply those together, you get Kw. So here you go. All you got to do is you're going to see on the next slide or the next thing, you're basically taking this times this. That's it. It's a proof. So here we go. The first term times the second term. It's like magic. I just think that is so cool. Allow things to cancel that are going to cancel. I know, isn't that so fun? So our HB's cancel. Okay, our B minuses cancel. And of course, what we're left with is, which that's equal to KW, isn't it? In dilute aqueous solutions. I love it. I love it. Equals KW. But that is a pair that differ by proton. All right. So if this is the deal, like if you, and it's funny because I guess they can just even be on a table. They don't have to be running around in solution together. But if you find any conjugate acid-base pairs, from the table, the Ka times the Kb will always be equal to Kw. Is that not cool? What? I love it. So like that thing we looked at before, all sorts of neat things, yeah. So if you just kind of go along, let's see, how does that work? No, maybe be a different one. It must have been one we looked at before.
Oh, yeah, that was a few days ago.
I don't know, yeah.
There you go.
Yeah, we're getting closer. Oh, okay.
Maybe.
Almost. Okay, so
Oh, wait, these, yeah, acid
Yeah.
conjugate base.
yeah, here, I think. Is this like, no, that's not. You need it to go
These
across.
acid and conjugate base?
Yeah, but you need to have the Ka
Oh.
and Kb values.
Um,
Yeah, but these don't go, these are different
Oh.
ones, aren't they?
yeah.
Ka, nope. I
Well,
guess,
that's
you know
it.
what this is proving? That, you know, you're not going to have a table that has both of them, because if you have one, you can calculate the other, knowing they multiply together, they equal Kw.
Okay.
So as one goes up, the other goes down, and as one goes down, the other goes up, because the product is constant. Nope, they're
So
all
there's
just
acids
Kas,
in-
yeah. Yep.
Okay.
But do you see where, like, if you wanted, so this is conjugate acid-base pairs are like these two right here.
Mm-hmm.
So the Ka of this is this number, and this is a good example. If you wanted the Kb of this, you just take Kw divided by that.
Okay.
Yep. That's it. So, yeah, this is one of the ones we looked at, and this actually kind of lists them out. Conjugate acid-base pairs, they differ by a proton. But there are no values here, you know. They're just saying that perchloric acid is a significantly stronger acid than the perchlorate ion, which could be a proton acceptor, is a relatively weak base. As you go down here, the ammonium ion is a much stronger base than the amide ion. Wait, I might got that mixed up. The amide ion is a much stronger base than the ammonium is an acid. Accepts a proton instead of that donating a proton. Actually, your homework, this table is going to be helpful, I think, for your homework. So, I don't think we'll get to the homework slide. But this is a classic, so I want to take just a minute to look at this. So what if you have all these solutions and they kind of make your eyes go buggy? How to arrange them in order of increasing pH, so increasing basicity. So your most acidic will be on the first one, okay? So increasing pH. What I would do if faced with this is I would go ahead and categorize each one of them. And you might not know, but hopefully it'll start to come to you. So for instance, ammonia, and I think, did you guys do home? Does it seem like it would be, well, this kind of gives it away. The fact that there is a KB, okay, means that it's a weak base. Okay, so it's a weak,
They all don't have that one.
right. So let's just go ahead and start there though. So what I would do in the margins is put WB, weak base. And kind of right after that, notice we have NH4 plus. Now, does this make sense? Actually, you can kind of look at these as a pair, NH3 and NH4 plus. That would be what, the conjugate, or the base and the conjugate acid.
Okay.
They differ by a proton. So, out in the margins of this guy right here, I probably would write conjugate acid, CONJ, conjugate acid of a weak base. Does that make sense? So this is one of the things to start thinking about. If you take regular old ammonium nitrate, we've got some in the storeroom, it's a solid. If you take regular old ammonium nitrate and go ahead and dissolve that, make an aqueous solution, what's going to happen is it's going to break apart, dissolve, okay, it's soluble, and your ammonium cation, NH4 plus, is going to go ahead and start acting like an acid. Now, it's not very strong because it's the conjugate acid of a weak base, and the conjugate is even weaker than the weak thing. Okay. Now, before I move on, and sometimes I guess I forget to tell students this, the NO3, I'm going to write spectator. Because if you think of what the options of NO3, it's an anion, NO3 minus, it's the nitrate, okay? Because do you think NO3 is going to form HNO3? HNO3 might ring a bell. That's actually nitric acid. So it's not going to form something strong like that.
Okay.
It always goes from strong to weak.
Okay.
Okay. So it's spectator. Formic acid, the Ka kind of gives it away. So what should we write over here in the margin for that one?
Weak acid.
Weak acid, WA. Yep. Nitric acid, what should we write in the margins for that?
Strong acid.
Mm-hmm, I sure would. SA for strong acid. Okay. So now the next one, sodium formate. So if we look at, I'm going to go ahead and take my Na plus and I'm going to write spectator again. Because your options are, it's a cation. Do you think it's going to form, let's see, it could go ahead and break up water and connect with a hydroxide ion. Do you think it's going to form sodium hydroxide? No.
I'm sorry.
Oh, do you think that it would react with a water molecule, your Na plus, react with an H2O? No. No. So it's just along for the ride. So the important part is this. Now, you may not recognize what that is, HCOO minus. But if you look 2 lines above, actually and it's kind of given away in the name, that formate and formic acid, formate and formic acid, actually they are a pair.
Okay.
So what
Yeah.
would we call that one?
The conjugate of a weak acid.
Yes,
Conjugate base.
very good. You got it. CONJ, conjugate base of weak acid. Perfect. You got it. What about the next one?
Yeah.
Can you imagine any chemistry, like pH chemistry? Do you think sodium hydroxide or nitric acid is going to form? It'll always go from strong to the weakest. That seems like an uphill battle, I think. I'll give you a
Right,
hint.
Yeah. Well, yeah, I guess that's where I was confused.
Yeah.
So,
They're spectators. By golly, if you take solid sodium nitrate and dissolve it in water, those things it'll be neutral. There's no effect. No acid-base chemistry. So this is the only one that's actually neutral.
okay.
And so what should we put over in the margin?
Neutral?
Neutral? Okay. How about the last one?
Okay, well, it has a hydroxide, so it's already, is it already a base?
So
Um,
is it a weak or strong base?
I don't know. I mean, if I had to guess, I would say weak, but I don't.
It is a strong base.
It is a strong.
Yep.
Okay.
Strong
No, I
base.
haven't memorized the list.
Yeah.
Yet, so.
Yeah, it is a strong base. And see, if I was faced with this.
Because it would break apart completely? Sorry.
Yes, yeah.
Okay.
And like the salts, that's a salt.
Okay.
Potassium hydroxide, sodium hydroxide, those are two common salts. Calcium hydroxide, maybe, they break apart and the OH minus just floats around, man, jacking up the hydroxide ion concentration. It'd be a one-way arrow dissolving it.
Okay.
Yeah. So I would do this first, and then so which one do you think is going to be the greatest hydrogen ion concentration?
Hydrogen concentration. The nitric acid.
I agree. Number one. How about the next one?
Formic.
I agree. Ding, ding, ding. You're 2 for 2. How about the next one?
I'm guessing the conjugate. Wait, the conjugate acid?
Mm-hmm.
Okay.
That's number 3. You're 3 for 3. How about the next one?
The neutral?
Very good. You've done this before, haven't you?
No.
How about the next one?
The conjugate base?
Mm-hmm. Number 5. Next one?
The weak base.
Yep. Number 6. And last but not
The
least, yep.
potassium.
Number 7. Yep. That's how I would work it. So that should match up with, you put strong acid first, strong base last, and then you put the weak acid, the formic acid, and then you put the conjugate acid of a weak base, and then you put the neutral, and then you put the conjugate base of a weak acid, and then you put the weak base, conjugate base, weak acid, weak base. Yep. Ding, 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 ding. So that's good. That would have been rushing too much to get through those next few slides. Yes.
Oh, no, I was.
Oh. So good question.